get started. So this is second consciousness talks. Thank you everybody for coming, and also especially special thanks to Aurelio and also Mohammad to take the speakers. I'll give a brief introduction to this consciousness talks initiative, and also two speakers one by one. So this consciousness talks is meant to facilitate the collaborative, interaction among the Asia Pacific researchers, and for that purpose, each speakers are expected to give a talk, a relatively short talk, 5 to 10 minutes, followed by 25 minutes to 20 minutes discussion, depending on the duration of the presentation, and then we go together. This top left thing here, this role-playing like thing. I'm going to paste the link and also password for the gather for the Zoom participants, and then eventually to YouTube participants later to facilitate conversation as well. You can ask questions to the speakers during the formal session and also informally at the Zoom as well. Okay. So first speaker today is Aurelio Cortese. You can see this his CV and bio and abstract on this
hey, now.
link. Yes?
Hey, you are not sharing your screen. So.
Okay. All right, good. This? Can you see the screen? All right, thanks a lot. And the link to this slide is available here, and also YouTube link as well. Aurelio is now an PI at ATR, and he used to work with, and also still quite actively collaborating with Mitsuo Kawato, Benedetto Di Martino, and also Hakuan Lau, who recently joined to RIKEN. And today's Aurelio's talk is about this non-conscious reinforcement learning. Please go ahead. I'll turn off the screen share.
Thank you now. So thank you very much for the introduction, and especially for the invitation to this series of consciousness talks, for this opportunity to present here. It's really exciting, I think. I hope you can see my slides and you can hear me well.
Yes.
Fine. Good. So yeah, today's presentation is essentially about choices, how we make choices, how we learn to make choices. And especially when it is about learning, choices actually play really a central role. And one framework that has been very successful at describing the way we learn to make optimal choices is reinforcement learning. So in reinforcement learning, usually you have an agent, for example, this mouse here, that is acting or navigating in an environment and as observations from the environment, and then as the opportunity to take some actions, to move around or to make choices or select actions. And in some cases would receive some outcomes. For example, it can be a reward, like a piece of cheese or cake. Now, this framework of that explains essentially how an agent learns to make choices based on the information from the environment. It's been really successful at describing behavior, biological behavior and biological learning. It is also successful as long as the environment or this space is not too complex. When things become very complex, we have what we call the curse of dimensionality, in the sense that it becomes very easy to know and to learn what is the optimal action, because maybe you have too many states, too many observations from the environment, or things are too complex. And so this creates really a little bit of a problem, especially if we think of, in general, biological learning or biological agents, where things are complex just by default. And at ATR, been pioneering for a while already, what we call decoded neurofeedback. I think this really gives a good example of this sort of complexity that happens in learning in terms of the brain. So in decoded neurofeedback, you have participants that essentially learn to induce a certain activity pattern in the brain. Now, when they do these experiments, they're not told what is the purpose or the scope of the experiment. They're just told that it is a game and that they have to learn rewards. But what we're actually doing in the experiment is that we're measuring activity patterns in the brain in real time, and we sort of compare this with a machine learning decoder to a target pattern. And whenever the two are sort of, you can say the two are similar, or the likelihood of the current one is close to the target, we get a high reward. So the brain here sort of has to learn a high dimensional mapping between this sort of complex activity patterns and this sort of unidimensional continuous reward function. Now, yet it works. We have already several experiences in terms of behavioral outcomes, so we can see that this technique can be used to change behavior. So in Shehata's original paper, they found that they could induce perceptual learning without ever showing those stimuli, just by reinforcing their activity pattern. In my own work, we modulated confidence, again, by reinforcing those activity patterns. But when you look at this, then it really sort of begs the question of, so how does the brain can resolve this kind of problem? Because this is really a high dimensional problem, and the brain is able to do this within a few hundred trials. And so if you can use actually this framework, this sort of real-time design of experiments, to test the idea on how humans can learn actually to make choices based on this high dimensional activity patterns or high dimensional problems. And then if you think that metacognition is actually sort of involved in, at least from the perspective of higher order representations, maybe prefrontal cortex, and sort of extracting lower dimensional representation, then we can hypothesize that maybe metacognition in this case facilitates this sort of learning. So metacognition in the end is what I would call here is a self-monitoring function, so monitoring our own choices or actions. And in the lab, we often measure it as a decision confidence, so sort of the certainty that my choice was correct. But we can also think that metacognition is involved in these higher order representations, maybe in the prefrontal cortex or in sort of, let's say, a higher order brain regions. And if so, then they might play actually a crucial role with this kind of learning. So the task that we designed here, we had participants viewed as dim, like a cloud of dim and randomly moving dots. So here there's no motion, there's no coherent motion. The dots are moving completely randomly. And we asked participants to make a perceptual choice, to rate their confidence in the choice, and finally to bet on two options, such that sometimes they can get a reward. They're just told that their goal is to learn which option they should bet on every trial so that they can maximize these rewards. What really happens is that during each trial, we are decoding the brain activity in either the visual cortex or the prefrontal cortex. And this decoded output is used to determine the task conditions, what we call here the reinforcement learning hidden state. So the decoder will output whether the representation, let's say, is a right or a left motion. And then this is used then to define this hidden state. By hidden state, I mean essentially it's used to define what is the optimal action. So if the decoder, the brain state, suppose is representing right motion, or this stochastic activity represents right motion, the optimal action is the A. And so this would be the one that if participants bet on that option, they would receive high reward, and vice versa for the other brain state. Now here I want to stress that participants, they do not know that this decoding takes place. They do not see any physically coherent motion. This is just activity, sort of a representation that is decoded from their brain activity. You could say as a sort of latent representation, non-conscious information that is sort of lingering there in the brain activity. And the decoder just outputs this label, right or left, that we use as a condition for the task. The experiment was done over 3 sessions. So the first 2 were with this kind of idea. The third one, we actually translated the motion, so the decoder output, into a motion direction. So now we sort of collapse this very high dimensional activity that is in a certain brain region into a very simple output, which is like motion to the right or motion to the left. And in this case, we can test if participants can explicitly learn the rule between seeing right motion or left motion and the optimal action. So you see in the third session, this is what the task would look like. So you have actually coherent motion before they can take their choices. So what we find is that, surprisingly or not so surprisingly in a way, already from the second session, in which there's no physical information about what is this hidden state, participants are able to choose the rewarding option, the optimal action, more than just by chance. So really we have the brain that is learning a sort of intrinsic mapping between a non-conscious neural pattern of activity and an action, really to get rewards. I think what is more interesting is that when we look at the an index of metacognition, we found that it was predictive of learning ability. So here in the x-axis, you have meta d prime, essentially how well confidence judgment track the correctness of the perceptual choice on a trial-by-trial basis. This was measured on what I call session 0, is a previous session that is not part of this learning experiment that was just used to construct the decoder. And yet, this initial metacognitive ability is predictive of the sort of baseline ability to choose the optimal action in the first 2 sessions. So we have a link between metacognition and this learning ability at the behavioral level. So because we have this at the behavioral level, now we can think we should be able to find a link at the computational level. So here what we looked at was because this is a learning task and it involves reward, the framework is reinforcement learning. So with reinforcement learning, what we can compute is this reward prediction error, so the mismatch between the agent expectations and what they will actually get after the choices, what is the outcome of their actions or the choices. And this reward prediction error, if you take the unsigned sort of version of it, is a sort of a measure of the uncertainty in the learning on a trial-by-trial basis. And what you find here is that already from the first session, but this effect gets stronger with learning, we have that there's a relationship between this behavioral, psychological confidence and this computational uncertainty. So meaning that when participants have a high confidence, they're also more likely to have an output that is closer to their expectations. When they're not confident, things look more different than what they expected. But because we have now this relationship at the behavior, at the computational level, we should also find some sort of neural correlate of it. And one way to look at this is, since we have this kind of strong coupling between confidence, let's say judgment, metacognition, and reinforcement learning processes, one way to look at it is to try to find if there is a increased neural coupling between the 2 brain regions that harbor the relevant signals. So dorsolateral prefrontal cortex for confidence signals and the basal ganglia for reinforcement learning processes. So we use a sort of a multivariate coupling, so the multivariate activity patterns in each region that was related to either confidence or prediction error. And what we see is that with learning, this kind of information coupling between those 2 regions really increases pretty strongly towards the third session when things are learned, end up being learning explicitly as an explicit rule. So with this, I've shown you we've demonstrated the human brain can solve a very complex multidimensional problem because the task itself is designed in a way that what defines the optimal conditions is a non-conscious brain activity pattern of which participants do not know about it, do not know the location. There is, again, all the noise of the fMRI and the decoding in play. So it really is a very complex problem that participants are able to learn within a few number of trials. Metacognition seems to play a substantial role in this, and we find correlates at the behavioral, computational, and neural level. And I think what is particularly striking is this increased coupling between those two regions that really harbor those signals that are related to reinforcement learning in the basal ganglia and the confidence signal in the dorsolateral prefrontal cortex. And so I think this really kind of opens a question as well in terms of metacognition, but if we look a bit more broadly, consciousness itself. So how important, how crucial is it for biological reinforcement learning? So you can think that one of its core function is to reduce the dimensionality of the space. So in consciousness, we can't hold that much information. So you can see the sort of way to constrain what the agent sort of is currently representing, currently also focusing on in a way. And this in turn, I think, could open interesting points of parallel into what do we become conscious of at the end of the day, especially if we think of it from this sort of learning perspective. And so with this, I would like to thank you all for your attention, collaborators who have done a lot of work in this as well, and funding agents. And now I'm happy to discuss, since there's a lot of things that probably I didn't touch or didn't cover.
Okay, thank you very much. Okay, great. All right, you got lots of upload. And does anybody have a particular question? You can raise the hand in Zoom, or you can also type in the chat the question. Or also you can speak out here as well. If not, then maybe I can also ask, as a sort of follow-up of what you said. So from the theory of consciousness, is there something that you particularly have some kind of interesting idea or conclusion from these results? Like the fact that you can decode the non-conscious information to use reinforcement learning. What's the sort of the relationship between the consciousness and let's say reinforcement learning in the artificial agent or something like that?
Yeah, I think that so as I was kind of pointing towards the end, is that so of course reinforcement learning does not need consciousness to work or to happen, and that is why we have super successful deep neural networks with that are trained with reinforcement learning, and that works really well. But the point is that they need a very high number of, usually very high number of trials, really high number of experience samples to learn like successful behaviors. So I think here, in terms of consciousness, could be if we are ever able to sort of design or reach sort of artificial consciousness, this could have as a direct effect, could have really to enable agents to learn really efficiently in a data efficient, but also time efficient and sample efficient way.
I see.
Now, also what this means in terms of consciousness and theories of consciousness. So I have worked a lot with Hakwan, and with time I tend to look at this work as well as a sort of, especially if I think of it in terms of this metacognition and the way that it seems to play out with reinforcement learning, this kind of interaction that happens really through learning. And although this work is not directly causal, because it's again, you have a correlation between all this confidence metacognition measures and the reinforcement learning sort of accuracy or ability to progress. I think there are a few points that kind of seem to indicate that metacognition has a really a kind of almost like causal role in this. And the reason for that, for sort of thinking about that, is within the task itself, the confidence sort of rating or the confidence judgment came before the actual reinforcement learning action. So sort of I see this as a way for the brain, using metacognition or consciousness, a way for the brain to have these meta representations that are low dimensional and that really enable reinforcement learning to operate more efficiently. Otherwise, the brain would be bound to use just basically simple sensory information, and that would take a lot of time because that's high dimensionalized complex.
Okay, thank you. We have 3 questions. Bowen, do you want to speak to ask question? I'm not sure whether we hear you. You are unmuted, but we are not hearing you. You are unmuted, but we don't hear you.
案に直訳すると2000歳以上を持っている。つまり、
I don't know. What was the sound? I don't know. Okay, all right. I'll read the question for Bowen. Would you identify consciousness with this hypothetical feature selection mechanism? That's the question from Bowen.
Yeah. Okay. Yeah. I think that so. In a way, yes. So probably consciousness is not the feature. It might not be the feature selection, or like it might not operate the feature selection itself, but it might be a way to keep those selected features sort of to represent them in a sort of in a brain region or in a way that is on which reinforcement learning can then operate. So consciousness might not be the feature selecting in itself. There might be other forms. There might be attention or other other bottom-up mechanism and so on. So I don't really talk about that here. But I think what consciousness can allow is that to have those features really readily available then for reinforcement learning. I think there's Joshua Benjo who wrote a short paper a few years ago on that, on what they call the consciousness prior. Sort of again to bring this idea that consciousness could be providing this kind of space in which you have those very few limited number of features that can be represented, and then that the agent can operate upon. But for that you would need so the idea would be that you need to have a re-representation, and that's what consciousness could allow.
So in a sense, what Bowen says about this feature selection mechanism corresponds to the first order mechanism in your higher order theory kind of thing?
Yeah, it could be seen as a first order mechanism, basically. Yes, exactly.
And according to your framework, that's not the part directly related to consciousness, but it's more to do with the meta stage that is relevant.
Yes, exactly. At least in my view here, in this kind of learning framework, or however, I would see consciousness as really as being this kind of higher part only. And then this kind of lower part, or this first order part, would be maybe dedicated to select those features, but you don't necessarily need to be conscious about them. They can be selected, but to be conscious about them, you need to re-represent them.
Okay.
And then it will be available also.
All right.
For simpler reinforcement learning.
I think that probably answers to Bowen. Fine. Next, Ariel.
Hi, thanks for the talk. I've just got a question about the variability of meta-confidence judgments for subjects within the sessions and then across the sessions. So my question is, unless I've misunderstood, they're improving the task across the sessions, but within session, presumably they have different meta-confidence for different trials, but they don't really know what they're doing. So my question is just, how variable is the meta-confidence for participants within a session on the trials, and then how much does it improve over time, even though they're not really sure what's going on?
So you mean in a way, so for the confidence, they have different they have those different levels, right? They have 1, 2, 3, and 4. So you mean how much do they use this range, or how much do they stick to 1 or 2 options, basically, right?
Yeah, I'm guessing just as they improve at the task, does their meta-confidence improve? How much does their meta-confidence improve? And is it just monotonically, or is it still quite variable across different trials, even as they're getting better overall?
So metacognition does improve with the learning. So in the sense that they become better at judging also when they are correct or not. And this becomes particularly strong in the last session. In the last session, you're in a sort of different regime, right? Because they can see this, so that they can see the stimulus, so they can see the thing. So the problem becomes relatively simple. In the first two sessions, which I think are the most interesting ones, you do see from the first to the second session, you do see a difference, and you do see in the second session you start to see a difference in. But this again, it's at the session level. But within the second session, maybe I have a. No, I don't have it here. Sorry. I thought I had a slide on that. But basically, already from the second session, you start seeing a difference in the confidence if you look at the trials in which they were correct and if you look at the trials in which they made a mistake. Now you have, if people are metacognitively able, you expect to see a difference in confidence. There should be more confidence when they're correct. What you see is that on the first session, it's basically completely flat. Second session, you start seeing a small difference, and on the third session, then you have a big difference between the two. So sort of that the two seems to go hand in hand. Sort of, they become metacognitively better, and they also learn to choose the better options to get rewards.
Thanks.
Okay. Mohammad?
First, thank you for that great talk. So if my understanding is correct, the first two sessions is kind of like more of a subconscious task, but the third session is more a conscious task. There is a difference between the first two and the third one. And did you notice any difference in neural correlates between the first two sessions and the third? So beside the decoder itself, do you have any neural correlates that can differentiate between subconscious and conscious one?
Yes. So there's actually a few things that we have looked at. So one of them was, and I think this was really quite interesting. Fortunately, again, I didn't put the slide here, I think, but there's another one that I can show you. So when we looked at the correlates of the prediction errors, so here this was not a sort of contrast or comparison between the first two and the third session, but it was just within each session looking at those prediction error correlates across the brain now. So looking for where do we find activity that correlates on a trial by trial basis with this amount of mismatch, or this like amount of surprise between what one obtained and what one expected. What you see is that in the first two sessions that are unconscious sort of learning, you see that those correlates are widespread across the whole, like really widespread across the brain now. On the third session, when you have this strong conscious component, now you have very few, very strong but highly localized correlates. Sort of as if in the first two sessions, you have the sort of the reinforcement learning process is really trying to find what is the relevant information, what is the relevant state. And because it doesn't know, consciousness probably helps with that, confidence helps with that, but it's not the whole picture. The brain is kind of looping, it has those loops across several brain areas with the basal ganglia. In the third session, when participants are conscious, now things becomes easy in a way, because you have the problem becomes like it's one dimension. You have two states and two actions. So things are really simple. And now you see that those prediction errors are very localized. That was one thing. Second thing that actually I have a slide here that we looked at was, so this is a functional connectivity simply between at the beginning of the second session, which is when the learning is still completely unconscious, and at the beginning of the third one, once they start to learn again. And here you see now this increased baseline resting state functional connectivity between the area of the dorsal prefrontal cortex, of the parietal, and the basal ganglia, essentially. So this two becomes more coupled. And lastly, now this is in terms of more dynamics in those two regions. So here I'm collapsing participants all together. And I'm doing, so here it's sort of a PCA, so principal component analysis of those activity patterns in each of these regions, in each trial, across the whole time course of the trial. For each participant in each session. And then looking at how, if you look at this sort of 2D distribution, so of the first two components, for each time point, you have one distribution for, if you collapse all participants, you have one distribution for each session. And then we can compare how different they are. So in a way you can look at how different is the dynamics of the activity we measure at each time point of the trial and across each session. And then we can compare them, and we have this baseline kind of what would happen by chance. But I think what is really interesting is what happens here. So this is actually the full trial time course. And what is I think most interesting is what happens at those two kind of time points. The first part is when in all sessions you have the just random motion. So this part is identical in all sessions, first, second, and third. This part here is when only in the third session we actually translate the decoding into motion. So here, this is when you have a difference between the first, second, and the third session. And what you see here is that these dynamics in those two areas start to look different based on the session, especially in terms of this conscious versus subconscious learning. What you have is that, sort of as expected, in the time point when in the third session we have sort of a stimulus that participant can become conscious of, you have the biggest difference is between the session 1 and 2 versus the third one. No? And on the other hand, when you look at this period here, where it's really when learning happens in the second session, now you have the biggest difference is between the first session and the two others. And I think this is really interesting because it tells us that, of course, here at this point, you have this kind of conscious experience of the stimulus. And so you can clearly differentiate the activity patterns within the area between the sessions. But here it also tells us that the difference here is really learning related. So that sort of, because on the second and the third session, we have more similar activity patterns or activity dynamics, then it tells us that this is sort of really a subconscious learning. I don't know if this really answers your question. I've given a lot of points. But
it answers. So are these differences localized in the prefrontal cortex, and is this the occipital? Or,
so here, so good point. For this analysis here, this is based on the two regions that were used for decoding in real time to determine the task conditions.
Okay.
So this is localized, either visual cortex or prefrontal cortex. But one could think of doing similar analysis with a searchlight, which so far we haven't done. But this would be an interesting next step to see if kind of the more global aspect of it.
I would also be interested. I didn't know that the sessions happened on 3 different days. Are these days just like consecutive, like day 1, 2, 3, or there was times in between? They consecutive?
No, they're consecutive. One after the other.
Yeah.
Okay,
I would be interested in knowing. This is fMRI. So if in the hippocampus, because it's a learning. So it's in within the short-term memory. So if there is difference in the hippocampus itself or not,
Maybe can I suggest that you go on to discuss about this in Gather?
In the Gather, okay,
Because we are now roughly like 30 minutes. And sorry, Kyofumi, Miyoshi, I also couldn't take your questions, but hopefully you can ask question in Gather. Is that okay? So let me now go to introduce next speaker. So next speaker is Mohammad, who just asked the question. Am I sharing my screen right now? Yeah. So
I can see this.
Mohammad already kind of revealed his background a little bit, but he used to work on hippocampus in rats when he was doing first PhD and also the PhD as well as also postdoc, right, in Kaori Nokchi's lab in Japan, Toyama University.
Yeah.
And then he made a really drastic move of the change of the field into study the team flow and team consciousness in Shin Shimojo's lab at Caltech. and that's all using human and also EEG and many different kind of signal processing, as you will see. So I kind of joined their project at the end to help the analyzing a part of the data, but it's basically quite detailed Mohammed's work. So please go ahead and Mohammed to tell us about this work.
Okay. Okay, I'm not sure if
Yes, we can see it.
okay, so I probably clicked on the right. So now can you see the slide itself?
Yes, very clear.
Okay, okay, I can't. Okay, now I see. Let me get the pointer ready. Okay, okay, yeah. So as now mentioned, this study is kind of a bit of a shift, but it's very interesting ride, moving from rodent. It was mouse, not rat, but because we did optogenetics and we can do this with rats. So, but it's very interesting to get kind of like both worlds of rodents and humans at the same time. So I'm gonna talk now about concepts called team flow. And probably you all know what the flow is, or getting in the zone. It's kind of a psychological phenomena revived by Csikszentmihalyi, who is a psychologist here in California in Claremont. And he revived this concept in the 70s, and it's make a good splash. And the main point of this talk of the flow state is when there is a high challenge of doing some certain task, and at the same time there is a high you have a skill level, then you fall into sorry I have an issue here, so give me a moment.
Oh, we can see it clearly.
Yeah, I have the there's an I can't see it, but it's probably here, around here. Yeah. So this is the flow state. Yeah, the challenge level and the skill level, when they are both high, then people start to fall under this state, which is the zone, and it has several dimensions that's mentioned, and I'm kind of like summarizing them here. You have an intense concentration and in high intrinsic reward and high sense of control, clear goals. And in my perspective, the most important signs of getting into the zone are these two here, which is losing the sense of time. So you just find hours pass like minutes. Anyone play video games definitely know this experience. And or doing scientific research also. Also like loss of self-consciousness. It's kind of, this is how they frame it, but it's kind of, you lose the consciousness of anything outside the task. So you have a very focused, you're very conscious about the task, but anything outside the task, anything irrelevant to the task, it's you become unconscious to it. Or less conscious to it. So there is definitely a lot of literature about the flow state and its neural correlates, but all of them have been studied into only in the solo flow or the individual flow. And as we are living in a very interactive world, even with the Zoom, we want to kind of like challenge and study the neural correlates of the interpersonal flow or the team flow. So just to in briefly in a rush, So this is the task that we used. I'm not sure if the audio will be working or not. Is it working?
Yes.
The audio? No?
Audio is
not.
Okay. Audio is not.
It's okay, yeah. So there is a music here in the background, and this is a very common game. It's called it's common genre of games. It's called the music rhythm games, where people usually tap at the bottom at a certain line. It's called the judgment line, and exactly when there are notes falling down. And it just gives the sense of playing a music rhythm, like a music instrument. It's not completely mapping, but it just gives you that sense. And there is a whole industry based on this game and how much is engaging. What we've done is this game is supposedly a solo game. We made it a team game. As you can see, there are 4 hands here. There are one participant is trying to take care of the 2 lanes. Another participant take care of the other 2 lanes, and they're completing the task together with one goal is just to get the best score for the team. And we kind of like hit all the scores except for these like fancy effects that give you a direct feedback that there is a correct hit or correct tap by the participants. And sorry, I need to go back to the arrow so I can this. So I'm talking about these fancy feedback. So by doing this task without going into details, we tried each group did about 6 songs on 3 different conditions. There is a team flow condition, which is exactly what's here. Another condition, we scrambled the music, so the enjoyment part already disappeared, and that would be only team. So they are going as a team together. And the last one is the flow only, where we just put a cardboard between all the participants. So it hides all the body and also the hands. So it's just cutting in between these the judgment line into 2 halves, but still the visual input itself is fixed. So they can't see the other partner hand or this feedback, the positive feedback. And we did high density simultaneous hyperscanning EEG with MRI registration for this experiment. And first, we just assessed that the flow state either subjectively. This is a common questionnaire that we send after each trial, which is about 2 to 3 minutes. And what we can see is we just averaged the questionnaire into a team flow index, and we can see that there is a clearly significant experience of team flow compared to the other 2 conditions. We also assessed the flow state still objectively. This is the first time someone does this, because we want to be sure that it's not only a subjective experience. And this is based on this loss of self-consciousness. While they are doing the game, we're sending an irrelevant beep sounds that looks like someone knocking the door, and we measure the auditory potential to this irrelevant beep sound. And we can see that when the participants were not listening, we're having this scrambled condition of scrambled music, and their flow state is disrupted. There is a high AAP, which means the brain response to the auditory, the irrelevant beep becomes more prominent when they are not in the flow state. So this is just a confirmation that we are reaching our desired state. Then we checked in more of like exploratory approach on the channel level if there is any significant difference between the conditions, and we found on the left temporal lobe in the beta gamma, there is in the beta gamma band, there is a difference in the power. And if you can see here that, yeah, if you can see, this is the team flow condition. So in the beta and gamma, there is a very clear difference between the team flow condition compared to other two conditions. Then we here is where now come in, and now and Angus, they help us do this analysis. So we also tested the integrated information, and we found that in the team flow condition, there is increased intra and interbrain integrated information compared to the other two conditions. Globally, it's significant only on the interbrains. And if we look to each brain area, I forgot that to say that we this is not a channel level data. This is a source localized data. So that's why they mapped into the brain. So we found that the middle temporal cortex is significantly higher in the integrated information within the interbrain integrated information, and only on the team flow compared to the other two conditions. We did also, I didn't show that here, we did also granular causality analysis, and there was a significant difference on the flow of information from the prefrontal cortex and the inferior frontal cortex to the middle temporal cortex. And another thing that we also analyzed is the interbrain synchrony, the phase locking value. And if we have, this is the paired participant, there is a significantly higher PLV compared to other two conditions. And if we randomize the pair, there is the difference disappear. And so far, what I have discussed is what are the neural correlates that we got out of this experiment. So mainly when I'm discussing this today with the consciousness talk is the first thing is based on this interbrain synchronization and the integrated information, I can say that when teams are in flow compared or teams not in flow, or they are flow but with lower team interaction, there is kind of like a special hypercognitive state or a special interbrain state. And this kind of like agree with other literature that's who detected interbrain synchronization and something like intense socialization or music production, or even just teams, regardless of they are in flow or not, teams versus an actual solos. Yeah. Also for the information, there was a paper, although this wasn't neural correlates, but they correlated the integrated information with the measure of collective intelligence. So the discussion point here, as we are in the consciousness talk, is whether actually team flow creates something that we can call like team consciousness. And I mean, I'm not the expert with integrated information, now can tell more about this, but what we found as a higher integrated information cannot be a definitive, what I can say, a definitive proof that there is something that we can say that it's a team consciousness. But at the same time, I would also argue that there is something that's, I wouldn't know how I can call it, maybe it's team awareness. So even with a very engaging task, this task is the participant has to kind of like tap within about 5 hertz, so like 5 taps per second. So it's very, very engaging. And just by hiding the positive feedback of the partner, but not their own, you can find a change being very clear neural correlate that's showing that difference. So definitely I don't have within the data collected now any proof or evidence that there is what we can call a team consciousness or not, but there is kind of like clues that there might be something related. I think that's will be it. I'm just gonna thank all the collaborators from Caltech and from Toyohashi, and definitely now and Angus from the Monash University. And this is the funding. Yeah, we also take this study to industry and NASA. They are interested in kind of like creating a real-time pipeline to monitor and monitor and modulate the team flow. And this is kind of like our current study, what we're currently doing. So I stop here and take questions if there are any.
Okay, thank you.
Welcome.
Okay, great.
Yep.
All right. So is there any questions from the audience? Yes, Aniko?
Yeah, thank you. Super fascinating talk. And yeah, I have a lot of questions, but I'm going to just stick to one. Have you checked the flow team performance and how the team members' performance related to the flow state and perhaps their neurocorrelates?
Yeah, wonderful question. Actually, yeah, we did definitely check the performance. So I would say the gross performance, because I didn't have this is not an open access, so I have to stop sharing. So this is not an open access game, so I didn't have an access to the exact timing, but the gross performance did not change across the conditions. This doesn't mean that the enjoyment did not change or the experience didn't change. Yeah, based on what we have as a gross performance, no, there was no change.
Okay.
I see. Thanks.
We have one question from YouTube, but also Aurelio, you are the first. So Aurelio?
Okay.
Okay, yeah. Thanks, Mohammad. That was fascinating, I think, really. I'm just curious to hear about maybe the interplay or so between the subjective, our own confidence and this team confidence. Because what you mentioned, that when you're in this flow, you have like self-consciousness kind of decrease, like is one of the signs, like decreases. But then when you're in this team flow, you have, so you kind of now you have consciousness more maybe about the team, about like So I was wondering, like, what are your thoughts about that?
So let me get actually, so you're asking about the relationship between the self-conscious and the team consciousness itself.
Within this, right? Exactly within this like flow kind of state or condition. If there is any interplay between two, actually, it does not have too much.
Yeah, I actually don't know if I would tell you my own experience itself. So especially with this game, with this level of high engagement, and it's a very demanding task, I would definitely have a very, very clear consciousness about myself. So I can tell you, yeah, I'm now doing good in the game, or no, I'm making lots of mistakes. But I would assume that that my consciousness to the team is more subconscious. So it's more like still there is a feedback that's coming into my retina from my participant feedback. Seeing the participant feedback, but it's it's unconscious, sorry, subconscious, and it's still affecting my performance. So I would give you some of the comments that when we were doing some pilots about the experiment, and some of the participants mentioned that this board is kind of like making a barrier, make me feel like in a barrier from the other partner. Also, participants sometimes can comment that if we also did matching, so to have a good team, you have to match the participant in their skill. They have to match the skill and interest, like the best song that they like. So in the first pilots, when we were not matching skills, so like a very skilled participant with someone not skilled, the participant who's skilled would complain. He said, this all disrupts my flow. I can't really play the game. So this means that there is a clear input. But I hoped I was consciously aware about designing the experiment in a way that I can do eye tracking, so I can see if they really gaze there or not. And I would ask a very specific questions about, do you actually notice the participant or not? Yeah, I mean, like the feedback of the participant or not, or just like design an experiment in a way that I can really track the conscious and the subconscious part. Yeah, but this is a wonderful question.
Okay. By the way, that separator reminds me of a Japanese ramen shop called Ichiran. Do you know? You're supposed to eat ramen, with a separator, and then you cannot watch any other person, eating. I wonder whether that enhances taste or reduces taste.
That's be very interesting, but I have you have to tell me about this ramen shop.
Yeah, it's called Ichiran.
Do you know why they're doing this? It's just like for privacy.
I think they don't believe in team flow.
Okay.
Anyway,
that's an overkill.
Okay. So the next question is from James in YouTube. I read it for you. He says, great. I wonder how this differs from hyperfocus in ADHD, where task switching is harder.
Yeah, that's a very interesting question. I would actually, I actually don't know. I can't really answer this question. I have
my guess is that probably hyperfocus. Hyperfocus in ADHD is probably something to do with more of the self-focus, right? Solo flow, probably. I've never heard of the ADHD more in the hyperflow with other people. So maybe if James can clarify this, that would be great. But Mohammed's study is more to do with the team flow.
And also, even if you think about even within a solo flow, so if within ADHD, I think the hyperfocus and ADHD, it might be a solo flow. It just that's why the ADHD have live in his own world and kind of like having enjoyment in this situation, but I'm not really the expert here, so I can't really relate I wouldn't tell that really it's a solo flow. The hyperfocus in ADHD is equal to solo flow or not. Even within the solo flow.
I'm not sure whether if we have any audience who is expert in this, but that sounds like more to do with autism rather than ADHD, but maybe I'm wrong. Anyway,
but it's a very interesting question. Very easy comparison.
All right. So James was saying, yes, you are right, that distinction between self and team is important. Okay. So Aniko, you said that you had a couple more questions, and we can take it unless other people have other questions. Go ahead, Aniko.
Yeah, so can you maybe share again your slides about the neural response, the EEG responses?
Yes, I'm trying. Do you see my slides?
Yes.
Okay, perfect.
Yeah.
So which slide should I go?
Yeah, I think this is the one. So
Okay, perfect.
I can see. So have you can you talk about a bit what your theory or what your explanation for the event related potential differences between flow only and team flow, if there are any? It seems
Yes.
like, especially in the early, like the P1 may be different.
So yeah, this is a very interesting question. So the AEP itself, when we designed the AEP, it wasn't meant to differentiate between team flow and flow. So whether you are a solo, less team interaction flow, or whether you are on a team flow, once you are in flow anyways, there is a decrease in the AEP as a response to this irrelevant beep. It's just as an observation that when we correlated with the flow index, the team flow index seemed to be much more correlated, like significantly correlated compared to the flow. But if you compare the correlation between the team flow and the flow only, that there's not they are not significant. There's no significant difference. So we would expect some level of, I would accept intuitively, there is some level of more of a team. So the flow level in team flow might be higher than the flow level where there's one participant only, or when the board was there. But I don't think the AEP actually captures this. It's not enough to capture the difference. Even with this correlation, difference in correlation, I don't think this can easily capture that.
Yeah, and do you think it would actually even more increase if you have multiple partners, so like a team playing some kind of sport?
Yeah, this is a wonderful question. I think so. I'm not sure if we have reached kind of like a plateau with the AEP, or no. We have to empirically try this. Yeah, so we're hoping in the future we can hire make more like a 4 team of 4 experiments. But this is a good question. I would love to try that.
Yeah, I heard that in UCL or somewhere in London, and also Max Planck in Germany, they are doing something like this, but using the music quartet, players, and also some kind of concert-like experience using up to 8 EEG sets or something like that.
Yeah. There are papers about this. So the only thing, so the reason we did not do the experiment with an actual music experiment is the artifacts that's produced by EEG. So that's why we tried this game, because and also in this game you have a control over exactly what's happening in the session.
Okay.
Versus the music stuff.
All right, that's great, and I think we are probably good to go together, and then discuss further. I just put the link and also password to the chat box, as well as also YouTube link. If you have further question, please go there and then talk a little bit more. Thank you, everybody, for joining, and hope to chat over there. See you. Thank you.